Hello, Chem 1A. This is Chapter 5, Lecture Video 5, and this is the last lecture video of Chapter 5. We're going to be talking about titrations. So titrations are another experimental technique. Usually we use a titration to do something called standardizing a solution, which is basically make the solution, then we standardize it to know its exact concentration. Or maybe we don't know what the concentration of an acid is in a solution or a base or anything in the solution, and we want to figure out what is the concentration of this known thing in the system. Well, we could perform a titration. This is where we add a known amount of standard solution. So we know this concentration of this thing, and we're going to add it until we see a reaction stop, right? That allows us to know how much of one reactant we put in the system, because that thing we're adding is reacting with something in our solution that we're trying to measure the concentration of. Usually we also add what's known as an indicator. This signals that the reaction has reached its conclusion. The reaction is no longer happening. We've run out of the reactant in the unknown solution that we're reacting. This happens when the moles of our standard, the thing we're adding, is equal to the moles of solute that's present in the system that we're trying to determine the concentration of. This is known as reaching the end point of the titration. And we can do some stoichiometry problems to figure out what the concentration, the mass, the molar mass of the substance was that we were titrating. Pretty much, like I was just saying, a titration problem is just a stoichiometry problem, except it's a reaction where we only really care about the reactants. We really don't need to know about the products other than to balance the chemical equation that we're working with. Just kind of give you like a visual image of this, right? In this container here, I have an unknown amount of, let's say, HCl. So we have HCl and we don't know what its concentration is. Up here we have NaOH in this example, and we know its concentration. Let's say the concentration is 1.00 molar, right? I'm going to continuously add NaOH to the HCl. I'll know the volume of HCl as well. Let's say it's 25 milliliters. And we're going to just keep adding the HCl or the NaOH to the HCl until we start seeing our indicators start to do something. So indicators tell us visually that the reaction has come to an end. The most common acid-base indicator, because this is an acid-base reaction we're talking about, right? NaOH and HCl, and that's the most common titration, is phenolphthalein. And phenolphthalein is clear in acidic solution and pink in basic solution. So as we add the NaOH, it reacts with the HCl. The HCl starts to go away. As we continue to add NaOH, the solution starts to turn pink, right? Now, after a while, that pink color sticks around and stays there. And so once we see this visual pink indication that the reaction has ended, we stop. We now are going to record the amount of NaOH that we added to the system. And since I know the concentration and I know the volume of NaOH that I added, using my molarity equation, I can solve for how many moles of NaOH were added. And I can use stoichiometry to back calculate how many moles of HCl were originally in the system. So let's do some example problems. Now, this is just a kind of cool infographic to kind of show you what's going on. Now, the primary way we've done stoichiometry so far in this chapter is we've used grams to get to moles. Then we get moles of A to moles of B using a mole ratio. And then either we stop at moles here or we go back to grams, right? Now, with molarity, we actually can use the volume of solution A and its molarity to get moles of A, and then we go to mole ratio, moles of B, and then we could go back to volume of B, or if we know volume of B and we know moles of B, then we can use these two to calculate our concentration of B, right? So number of different things we could do with molarity. It adds an extra dimension to our stoichiometry problems. So let's do some of those problems. So let's say we're talking about what volume of 0.6 molar acetic acid is required to neutralize 25 mils of 0.175 molar calcium hydroxide. Now, at the end of the day, titration problems are stoichiometry problems. So the very first thing we need to do is we need to write out that balanced chemical equation. We know acetic acid is going to react with calcium hydroxide. This is a double replacement reaction, so our products are going to be calcium acetate and water. We then need to balance it. That's what these 2's are for. And at this point, let's list out the stuff we know, right? So I know the concentration of my acetic acid is 0.6 molar. I know the concentration of calcium hydroxide is 0.175 molar. I know that I have 25.0 milliliters of calcium hydroxide. And we want to know what volume of acetic acid we need to get rid of all of my calcium hydroxide. So let's start with that 25.0 milliliters that we have, because if I want to figure out the volume, I know the molarity of acetic acid is 0.600 moles of acetic acid over liters of solution. Well, I want to solve for liters of solution. This means I need the moles of acetic acid. To get moles, I first need to figure out how many moles of calcium hydroxide it is that I'm trying to neutralize. So I need to convert my 25 mils to liters, right? We know there are 1,000 milliliters in 1 liter. And then, after having done that calculation, I know that 1 liter of calcium hydroxide solution is 0.175 moles of calcium hydroxide. And I know this because molarity is moles over liters, and we were given the molarity. Next, I'm going to do a mole ratio, right? I know that 1 mole of calcium hydroxide is going to react with 2 moles of acetic acid. And then lastly, I know that this mole ratio here, or the molarity, I can use as a conversion factor. I can go 0.600 moles of HC2H3O2 gives me 1 liter of that solution. And if we hit equals here, we're going to get liters of the solution that would be required of acetic acid to get this thing neutralized. This gives me about 0.0146 liters. Or, if we convert back to milliliters, 14.6 milliliters would need to be used to neutralize my calcium hydroxide. Now, this is the general scheme of titration problems. It's still a stoichiometry problem. It's just how we got to moles that changes. And if you had wanted to, you could have also used the equation molarity is equal to moles over liters to kind of take this guy, plug it into liters, put it here, take this guy, this is your molarity, plug it there, solve for moles, and then do a mole ratio if you wanted to. I just think this is more straightforward and streamlined. So let's talk about what if I asked a different question here. What if instead of asking for volume, I asked for what the mass of acetic acid would need to be that's added, right? Well, that's not really that much of a different problem. So if I'm asking for what mass of pure acetic acid would be required, the biggest difference is actually this last step, right? If I wanted to get mass instead of volume, I wouldn't use molarity of the acetic acid. I would use the molar mass of acetic acid. So let's replicate this entire line of calculations, but then we'll change it just a little bit. Okay, so here we have up to where we got to last time. This is where the difference occurs, right? I've gotten, if we look at this out, milliliters have canceled, liters have canceled, moles of calcium hydroxide have canceled, and I am now in moles of acetic acid. If I want to calculate grams of acetic acid here, I need to multiply by the molar mass of acetic acid. The molar mass of acetic acid is 60.06 grams of HC2H3O2 per 1 mole of HC2H3O2. Right, and finally this cancels the moles of acetic acid and we're left with grams of acetic acid like we were asked for. This gives me about 0.526 grams of HC2H3O2 are required to neutralize all of that calcium hydroxide. Okay, so let's do one last example. This is more commonly what we see for titration problems where we're trying to determine an unknown concentration, right? So a solution of HCl with a volume of 25 mils is titrated to the endpoint with 0.25 molar sodium hydroxide. It takes 34.56 milliliters of sodium hydroxide. What is the original concentration of HCl? Right, so I want the concentration of HCl here. I know that's going to be equal to the moles of HCl over the volume of HCl in liters, right? Well, I know this value in milliliters. We know that we have 25 milliliters of HCl. This gives me approximately 0.02500 liters. So I have this value there. What I really need is the moles of HCl present in the system. And I can get that from the NaOH volume and the NaOH concentration, as well as finally the balanced chemical equation for this reaction, right? So let's write out that reaction. We know that HCl, aqueous, reacts with NaOH, also aqueous, to give us two products, NaCl, aqueous, it's soluble, plus water in the liquid state. Now this is balanced already. It's a 1:1 to 1:1 mole ratio for our reaction. Now let's do our calculation, right? We know that 34.56 milliliters of NaOH was used. We know that we got to convert that from milliliters to liters first. Then we know that we have a 0.250 moles of NaOH for every 1 liter of solution used. Finally, we have 1 mole of NaOH reacts with 1 mole of HCl. At this point, we're going to stop because I need moles of HCl so I can take it and plug it into my equation up here, right? So let's do this calculation and get our value. We get that there are 0.00864 moles of HCl formed or reacted in this problem. So now let's do our final calculation. We have HCl's concentration is equal to 0.00864 moles. All of that divided by 0.02500 liters. And this will give me my final concentration of the HCl in the system, which is going to be 0.346 molar. Now, that is how you do a titration problem. Again, it is a stoichiometry problem. If I see any of you using M1V1 is equal to M2V2 to solve any of our calculations for titrations, I will give you exactly 0 credit for that problem. This is a dilution equation, not a titration equation. It doesn't work every time, and the units do not cancel when you use this equation. You need to do mole ratios when doing titration problems. All right, so this is the end of Chapter 5. If you have any questions, please come to a Zoom meeting in my office hours or email me and we can set one up, or email me the question.